Alrighty, so let me hide this. Now that we've gotten that Desmos out of the way and you guys kind of got a sneak peek at what we're going to be talking about since you did the Ed puzzle already, we got to address the elephant in the room, right? What is a distribution? And the long of it is essentially the distribution of a statistical data set is a listing or a function showing all of the possible values of the data and how often they can occur. So what happens is we organize it, usually from smallest to largest. We break it up into groups if necessary, and then we kind of start to categorize them. We put them into a graph or a chart, and then we start looking at like, what is its shape? Where is its center? Based on this information, what's the variability in the data? What can I infer from this data? So if you guys take a look, see over here at this like little distribution graphs thing, this is a normal distribution, Gaussian distribution. This is a bimodal where there's two modes, aka two peaks, something with a positive skew, negative skew. We'll talk about that in just a second. But there are so many distributions. We are primarily going to be talking about a normal distribution or distributions with positive or negative skews, left or right skews, right? But I just wanted you guys to know that there are so many different distributions in statistics. There is uniform distribution, which is where it's like all the same, which is this little guy down here. Let me get my laser pointer. This is a uniform distribution. There are triangular distributions. We have exponential distributions. There are Gaussian, which is the normal distributions. We have Cauchy. He's a famous mathematician. Cauchy distributions. We have gamma distributions. So many different distributions out there based upon like what you're looking at. So it's not just normal, but what we will be looking at and what a majority of the things that you quite honestly will be studying is normal distributions, which is why it's important. All right, so like I said, there's so many different, there's dot plot distributions. We started off stats talking about dot plots, right? So, you know, there's a dot plot. This is for the sugar in amount of children's cereal, I think. And if I were to create a distribution of this or wanted to see the skew of this distribution, this tells me that, wow, this number 3 has a lot of sugars there. And if I wanted to create a distribution, I could easily say like, oh, well, that's what my curve is going to look like. Or for this, an exam score, right? We could see a lot of people did pretty good around the B range here, and I could kind of create a distribution or a curve that matches this distribution and make inferences about that. Another very common distribution that you're going to see is bar graphs or histograms, right? This one's beautiful. I just thought it was so pretty. But this is for arrivals of something. These are other bar graphs, right? You can see that these ones are all a little bit different. They all have different types of data going on with them. This guy right here has two modes. It's multimodal or bimodal, right? But I could kind of make a little camel-looking graph based off of that guy. Here's just a ton. Like it literally can be anything depending on what you're asking, depending on what you're looking for, depending on the data, the results. It can be all kinds of different things. So thinking about distribution can be represented in the forms of dot plots or bar graphs, but just trying to figure out what's going on with the data, which data out of these two options, distribution A or distribution B, do you think has a larger standard deviation? And the dashed line is going to be representing our mean. So notice that the means are off between both of them. They're on the same scale, but they're off. So take a second and think to yourself. Maybe pause this video, look at distribution A and distribution B, and figure out which one has a larger standard deviation. I noticed something about A right off the bat is there's a lot more, or it seems to be a lot more dots, right? I have them extending as far as 0 and all the way up to 10. And something I notice about distribution B is I don't have anything down here. It's blank. I start at 4 and I go to 9. So is my data more spread out on distribution B, or is it more clustered together? Yeah, we can kind of easily see that distribution B is more clustered together, meaning that it would have a lower standard deviation. Therefore, distribution A has a higher or larger standard deviation because simply we can see from this graph that it's more spread out, that the data is not hanging close to that mean value, that dashed line. Something I wanted to bring up too, where we can start to view something called skewness, is in our good old box and whisker plots that we also started out with at the beginning. So it's a way to display data, right? It was this great way to visualize what was going on. We have quartile 1, quartile 2, quartile 3, quartile 4, right? These also can show you what your data is doing. It can show you how it's distributed, what the skew looks like. So this came straight from the video that you guys watched, right? So normally distributed data has exactly the same size boxes, right? They have the same size whiskers, same size boxes, and this is what the graph looks like. However, when we get into skews, a positive skew looks like this: a smaller box on the left, larger box on the right. Negative skew has a larger box on the left, smaller box on the right. And then notice that their whiskers are opposite. So the long whisker is on the same side as the long box and vice versa. But this is what it looks like. So box plots can show us distributions as well and can be translated from the box plot to a curved graph. Something to look at as well, this is just the curves of those box plots, right? If something's left skewed or negatively skewed, notice that the mean is really low, medium's in the middle, and the mode is higher. For normal distribution, mean, median, and mode are all equal. And for the right skew, the mode's the highest. It's the opposite of the left skew. Median's in the middle and mean is to the right. So when a distribution is skewed, the mean, median, and mode are not equal to one another. This is usually by some sort of outlier. So if it's right skewed, there's a really, really large X value. If it's left skewed, there's a really, really small value in the data set. And that's what kind of creates the skewness that we're talking about, the skewness that we're observing within these distributions. So as we start talking about what they look like, it can be a little challenging to determine if it's left or right skewed or positively or negatively skewed. So I saw this image and I just thought, wow, that's really nice. So if something is symmetrical, it would be like two kangaroos looking in a mirror image of themselves. They have a small amount on the left, the kangaroo up here, there's his head, and goes back down to the tail. I chose this image specifically for the tail because it's really nice. So this is symmetrical, right? Which is going to be a characteristic of a normal curve, right? It has the same thing on the left as it does on the right. Now, if you have a negative skew, where you have this long bit on the left and then you have a bunch of data chilling on the right, you can see that the kangaroo's tail is on the left. So if the tail is going to the left direction is negative, this is a negatively skewed graph or a left graph. But we call them negative. So I wanted to bring this image to our attention because I feel like it does a really good job of demonstrating that. And similarly, if we have a positive skew, the tail is facing the positive direction, but a bulk of the data is on the left, it's going towards the right in the positive direction. This is a positive skew. The tail is going towards the right. So the tail is the area that doesn't have a lot of data points. So this kind of leads us right into like normal distribution characteristics. This is the most frequently occurring distributions that we see in a lot of phenomena, such as like body weight, height. A lot of biological things happen to and in normal distribution curves. But some characteristics of it that you need to know is that it has this interesting bell shape. So notice that this kind of looks like the Liberty Bell, or I don't know, any other bell, right? It's got this bell shape. It is completely symmetrical, meaning that right down the middle, that's our mean, right? There's exactly the same stuff on the left as there's on the right, just like those two kangaroos. If there's 50% of values data on the left, there has to be 50% of data on the right. The mean is the same as the median, which is the same as the mode, right? So the mean is your average. That's right in the center. That's the center of our data, measures of center, right? But my median is also going to be the same as that. That splits my data completely in half, right? Remember when we talked about a median, we said it's like separating the freeway from northbound and southbound, right? Exactly 50% of the data must be on the left and 50% of the data must be on the right. That makes sense with symmetry. And then mode, which is the most frequently occurring value, would be the reason why we have this single peak here, right? So the mean is my center, it's my average. The median is exactly smack dab in the middle, my center, and the mode is how frequently something happens, leading to this single peak here, which gives us this bell shape. So the fact that the median is equal to the mean, which is equal to the mode, results in this perfect symmetry that we have and results in this perfect bell shape that we have. Something else to note is normal distribution characteristics are asymptotic, meaning that on the right-hand side, this is getting closer and closer and closer to zero, but never quite approaches it. And on the left-hand side, it's getting closer and closer to zero, but never quite approaches it, because we're actually using this normal distribution to account for all possibilities, infinitely many possibilities. And so since there's infinitely many, we can't get close to infinity. So it just gets really, really, really close. And we have found these approximations that will help us in determining like probabilities and different values based on if something has a natural normal distribution. Also, something to note, which we're going to get in a little bit more next week, is with a normal distribution, because it's completely symmetrical and asymptotic, 68% of the data lies within one standard deviation, which is a lot, right? No matter how far that, one standard deviation of the mean, there's going to be 68% of your data. 95% of your data lives within two standard deviations, and 99.7% lies within 3 standard deviations. So we'll talk more about that in a little bit. That's actually, called the empirical rule. But a little bit as in not today, next week. We'll touch on that a little bit more and do some stuff with it. So like I was saying, here's that normal curve again, right? Our normal distribution. Here is our mean, our center, right? Our mean is equal to our median is equal to our mode. And here's one standard deviation from that mean. The distance is 1 from the mean, and this is in the negative direction, so this is going towards the left, right? And within these two, this area right here, below this curve, this little chunk right here, 68% of your data falls within there. Within 3 standard deviations, you'll see that this is covering almost the entire curve, except for these little itty bitty bits here. That's why it's 99.7%. So let's do something with this, shall we? It comes up so often. We're actually going to start off with a pretty chill example, though. So this bar graph gives the weights of a population of female brown bears. The red curve shows how the weights are normally distributed, about the mean 115 kilograms. I really hope that's kilograms. Yeah, okay. I was going to say, I have no idea. The metric system. Approximately what percent of female brown bears weigh between 100 and 129 kilograms? So notice that we have this bar graph, right? Just like I was talking about, that's a distribution, and we can approximate it by this normal curve. I can see based on the bar graph and how it is set up that this is the curve that best fits this distribution right here. So I'm going to use that to my advantage. I'm going to use the fact that it is a normal distribution, which means it has symmetry, right? But it wants me to know what percent of female brown bears weigh between 100 and 129 kilograms. So I kind of have to look at my graph first, which can be challenging to analyze a graph, but I promise it's not that bad. So I noticed the x-axis is weight, and I'm like, okay, it wants me to know how many bears are between 100 and 129, right? So this chunk right here, that's 100 to 109. Then this next bar right here is 110 to 119. And then this guy also kind of in the center is 120 to 129 kilograms. So I really want this bar, and this bar. Okay, one step handled. Then I look on my y-axis and it has the percentages of bears. So this isn't going to be super exact because notice the scales in 10, 20, 30, 40, 50. So I'm going to have to estimate a little bit, but that's what I need because I'm actually looking for the percent of female bears. And they even say approximately, so they know it's not going to be super accurate. It'll be close, but we can't be too sure. So I know I'm going to use that first, second, and third column for sure. And the y-axis is the percentage of bears. So let's just estimate how much each column is and use that to figure out how much the bears weigh. So I noticed that if I look at this column, it's in between 20 and 25. So I'm going to say maybe that's about 23%. Then I'm going to look at my next column and I notice this is a little bit above 40, but less than 45. So I'm going to say maybe that's like 42%. It could be 43. It doesn't. It's an approximation. 1% isn't going to kill you. And then this last one is also between 20 and 25, but because it's a normal distribution, they're symmetric. So this side has to match the other side. Hence, I'm going to have 23%. So if I want to know what percent of female brown bears weigh between 100 and 129 kilograms, I could just add up this percentage plus this percentage plus this percentage. So if I do that, 23% plus 42% plus 23% is 88%. So in this chunk right here, which is a pretty big chunk, I can say that about 88% of female brown bears weigh between 100 and 129 kilograms. Pretty cool, huh? And not even that bad. All right, so what if I asked you guys to sketch a normal curve? That's okay. It's still going to have that shape. Check it out. It's got to have this shape to it. And I promise the more you guys practice, the better you will get. So the first deal is to get the mean if it's not already given to you. Oftentimes it's already given, but if you don't have it, if you have like a data set of something, get the mean. I showed you guys how to use Desmos. Use that to your advantage. Then determine the standard deviation. Sometimes this is given in like pictures, sometimes it's given in a table, sometimes it's straight up just given to you, but we need to make sure that we have the mean and the standard deviation because the way we're going to sketch this curve is I need to use the standard deviation. Then we're going to draw a vertical line at the mean and label it. Labels are super important. Then we're going to draw vertical lines on either side of the mean for the standard deviation and label it. And we're going to continue this on both sides. So after I've done one standard deviation, I'm going to do a second one on the right, label it. Same thing, I'm going to go to the left side of my graph, go to a second standard deviation, draw a vertical line and label it. Continue this until you have all the standard deviations you've been asked or given. And then lastly, sketch a normal curve that kind of matches it. So you're not usually going to have a bar graph to go along with this. Usually you'll just be given raw data, raw information, and then you will be sketching a normal curve or a skewed graph curve or something like that. Okay, so sketch the normal graph for the following distribution. Label the x-axis at 1, 2, and 3 standard deviations from the mean. So I know I got to do all 3. So here's some data for the average age of pregnancy in women. The mean is 32 years old, so on average, a woman's about 32 years old when she's pregnant, and the standard deviation can be 3 years. So the first thing we gotta do is get the mean. Luckily, the mean's already been given to us. So let's draw a vertical line for 32 years. Right, there's our vertical line. Our mean, I'm going to label it, and it's 32. I could have written years, but I was kind of running out of space here, running out of real estate. Okay, and then the next thing we needed to determine was the standard deviation. Luckily, in this case, the standard deviation was given to us of 3 years. So I'm going to mark out a little bit of spacing for 3 years, draw a second vertical line. 32 plus 3 is 35, so that's my label here. And this is 1 standard deviation plus 1 sigma. Remember, sigma stands for standard deviation. And then I'm going to do the exact same thing on the left-hand side. So I'm going to have my spacing of 3 going towards the left, which is a smaller number. So 32 minus 3 is 29. And this is negative 1 standard deviation in the negative direction. Then I'm going to repeat. I have 1 standard deviation down. I need 3. So I know my standard deviation length is 3. So I'm going to have another 3 right here, or you could add 6 from the center, because 3 plus 3 is 6. And 35 plus 3 is 38. Draw my vertical line. This would be 2 standard deviations. Do the same thing on the left. 29 minus 3 is going to give me 26. This is minus 2 standard deviations, or 2 standard deviations in the left direction, right? Because this is the center, the absolute center. And I just need 1 more standard deviation. So I know that the standard deviation is 3. I'm kind of just putting this here to demonstrate that the standard deviation is a constant value. It does not change. So 38 plus 3 is 41. So I've got my third standard deviation marked with the vertical line. And lastly, I'm going to do 26 minus 3, right? Because the standard deviation is still 3. So 26, 25, 24, 23 is my standard, is my new marker at my third standard deviation on the left. And once I have this, I'm like almost done. It's really just a counting game. You can use a calculator if the standard deviation is a little bit of a weirder value. But the last thing to do is to sketch a curve. Now, I'm doing this on my computer with no mouse. Don't judge me. And just like I won't judge you guys. It can be hard to start graphing a normal curve because it's a little different, but I promise with practice, it will get better. So I know that my normal curve eventually has to go up. It peaks at the mean, and I try to make it as even as possible. That was pretty good, actually. Pretty impressed. And yeah, that's kind of what it looks like. It's still got that bell curvy shape. The most important part is to try to make it even on the left and the right and make sure that this is the highest point that it goes. The mean is the highest peak. You don't want it to look a little wonky while we're out and about up there. Cool. So I talked about this in the Edpuzzle video, but just to bring it home, standard deviation measures how far away we are from the mean. How far is any of our data away from the mean? So these all 3 value graphs of these are the normal curve. Okay, and this is sigma is equal to 5. Remember, sigma means standard deviation. So this means that sigma was 5. And it's pretty pointy. It's pretty slim, right? He's chilling. He's pretty pointy up here. But the sigma is equal to 5 is a relatively low number. So that tells me that my data is not really that spread out. It's really, really clustered around my median and my mode and my mean, because they're all the same thing. That's the center of my graph, right? Notice that they all have the same area for the peak at 100. Their mean, median, and mode is all right there. Now, if I increase my standard deviation from 5 to 10, it gets a little bit wider, right? My data is a little bit more spread out. Now, if I go even further and increase my deviation from 10 to 20, I'm really pushing out my data. Notice that they all extend, but check out how much more the red graph is spread out versus the blue. Like it's incredible. You can really start to see the spread. So that's why visuals are so important. Not only can we see the spread on a box plot, we can see the spread on a distribution curve, we can see the spread on our dot plots, right? Visuals are really, really nice so we can get an idea of if the data is close to the mean value or not. Notice that the larger standard deviation, the more spread the data is, and the flatter that the curve is. And then something to just touch on really quick, because those of you that are taking stats, is z-scores. So when you get into probability, because probability goes hand in hand with stats, you're going to come to this point where you're going to be using these crazy charts. And this is what one of the charts looks like. So basically, you're going to come to a point where you're going to need to use a z-score. And you're probably going to be so knee deep in your stats that you're not even going to really know like what you're doing. You're just going to follow a procedure, right? But a z-score is a representation of the number of standard deviations from the means. So this is huge in probability. It's also measuring the area underneath a curve. But like, for example, you might be asked, like, what's the probability that you randomly chose a student's test and they got 85 or higher on the exam, right? That question can be answered by using a z-score, where you go and find the z-score that you're given, figure out like maybe it was 1.04. So you go over here, you get this value, and I forget what you do after, but you do something with it. I think you plug it into a formula or something like that, and it will help you figure out the probability that a randomly chosen student out of a class of 38 got an 85 on the exam or not. So the shaded area represents probability, right? The z-score represents that probability. Remember, our mean is right in the center here. So this guy's to the left. Sometimes we have to do addition. Sometimes we have to do subtraction. This one would be subtraction. This guy is addition. You can see that the area is much more colored over here. And sometimes you're given the tails. Sometimes you're given in between to figure out. Sometimes it's the opposite in the tail. So that's just another major application that if you guys are taking AP Stats, you will probably definitely be encountering some z-scores. They're pretty cool. They're not that bad. All right. I will. Yeah, I'll keep them. Yeah, I will see you guys soon. Thanks so much. And hope I didn't overwhelm your brain.